In this video, we are going to work through 3 different conservation of momentum practice problems in physics. So let's go ahead and jump right into this first example. This says, a 71 kilogram boy throws a 6.4 kilogram rock horizontally with a speed of 10 meters per second. Find the velocity of the boy immediately after throwing the rock. So let's sketch this out. We have this boy, he's throwing a rock at a speed of 10 meters per second. And our question is, what will be the velocity of the boy immediately after throwing the rock? So in this example and in the upcoming examples, we're going to be dealing with situations in which we have a system of objects, so in this case the boy and the rock, and there will be no external forces acting on these objects. So what that means is that the momentum in the system is going to be conserved. So what we can say in this situation is that the initial momentum, and momentum is denoted with a lowercase p, must be equal to the final momentum. Now, the initial momentum, that's going to be the momentum of the boy plus the momentum of the rock. And the final momentum will be the final momentum of the boy plus the final momentum of the rock. Now, momentum is calculated as mass times velocity. So what we can write is that the mass of the boy times the initial velocity of the boy plus the mass of the rock times the initial velocity of the rock must be equal to the mass of the boy times the final velocity of the boy plus the mass of the rock times the final velocity of the rock. Now, in this situation, the boy and the rock both start from rest. So both of these initial velocities are 0, and this whole left-hand side is actually equal to 0. So what we end up with is 0 is equal to this quantity on the left-hand side. And what we're trying to solve for is the final velocity of the boy, so this value right here. So let's go ahead and solve for that. So we can start by moving this quantity to the left-hand side. So here's what we get. This will be a negative quantity, is equal to the mass of the boy times the final velocity of the boy. And to solve for the final velocity, we just need to divide both sides by the mass of the boy. So what we end up with is these cancel out and we're left with, so let's write that right here. The final velocity of the boy is going to be equal to this quantity right here. So let's go ahead and fill in the values that we know. So let's see what we get. We have negative, the mass of the rock is 6.4 kilograms. And the velocity of the rock, the final velocity of the rock, that's 10 meters per second. So we'll say times 10. And then we're dividing that by the mass of the boy, which is 71 kilograms. So if we simplify a little bit, in the numerator we get negative 64 over 71. So negative 64 over 71, if you punch that into a calculator, that comes out to about negative 0.901. And we're talking about velocity, so our units will be meters per second. So that will be our answer for this one. So what that's telling us is that the final velocity of the boy is going to be in the negative direction. And the reason is because, as we stated earlier, the initial momentum must be equal to the final momentum. And because the boy and the rock both start from rest, if this velocity is positive, then this velocity must be negative in order for these two to add up to 0, which was the initial momentum. So that's our answer for that one. All right, let's check out our second example. This says, a 12,000 kilogram railroad car moves east with a constant speed of 18 meters per second. A 5,000 kilogram load, initially at rest, is dropped onto the car. What will be the car's new speed? So let's sketch this out. We have this railroad car, and initially it's at 12,000 kilograms. And it's moving east at 18 meters per second. And we're saying, okay, let's drop a 5,000 kilogram load onto this car. So let's say we have this 5,000 kilogram load being dropped directly onto the car. And our question is, what is this new velocity going to be once this load is dropped onto the car? So in this case, because the load is being dropped directly onto the car, there's no force that is affecting this car in the horizontal direction. So in this scenario, again, momentum is going to be conserved. So once again, we can write the initial momentum in this system must be equal to the final momentum. So the initial momentum, that will be the mass of the car multiplied by the initial velocity of the car. So let's say the mass of the car times the velocity of the car. And that must be equal to the final momentum. So the final momentum is going to be this new mass times this new velocity. So we'll say the mass of the car, the new mass, times the new velocity of the car. So let's go ahead and fill in what we know. The mass of the car is 12,000 kilograms to start with. And we're multiplying that by the initial velocity of the car, which is 18. And that must be equal to the new mass of the car. That's going to be the 12,000 plus the new 5,000 load. And then that's multiplied by the final velocity, whatever that happens to be. So notice, to solve for this final velocity, we just need to divide both sides by this quantity right here. So here's what we get. The final velocity of the car is going to be equal to 12,000 times 18 divided by 12,000 plus 5,000, that's 17,000. And if you punch this into a calculator, this comes out to about 12.7. And we're talking about velocity, so we'll say meters per second. So that will be our final answer on this one. Now, if we think about this scenario, it makes sense that this final velocity is going to be less than the initial velocity. Because remember, our horizontal momentum is not changing at all. So we still have the momentum is equal to the mass times the velocity. And if this value isn't changing, and if this mass value increases, then in order for this momentum to stay the same, the velocity must decrease, which is exactly what we saw here. So that will be our final answer on this one. All right, let's check out this last example. It says 2 ice skaters who are initially stationary push apart. Skater A has a mass of 72 kilograms and skater B has a mass of 64 kilograms. Skater A moves left with a velocity of negative 0.20 meters per second. Find the velocity of skater B after pushing apart. So we have these 2 skaters, and initially they're at rest, but they push apart from each other. So let's call this skater A and skater B. We're told that skater A moves left with a velocity of negative 0.2 meters per second. And our question is, what will skater B's velocity be? So again, we have a scenario where there are no external forces working on this system, so we know that the momentum is going to be conserved. So we can say that the initial momentum in this system must be equal to the final momentum. Now the initial momentum, that's going to be the initial momentum of skater A plus the initial momentum of skater B. And that must be equal to the final momentum of skater A plus the final momentum of skater B. So again, we can write for momentum, we'll say the mass times the velocity plus the mass of skater B times the velocity of skater B must be equal to the mass of skater A times the new velocity of skater A plus the mass of skater B times the final velocity of skater B. And in this situation, we're told that the skaters are initially stationary, so they're not moving. So both of these velocities are 0, and this entire left-hand side is equal to 0. So we have 0 is equal to this quantity right here. And our question is, we're trying to find the final velocity of skater B. So to solve for the final velocity of skater B, let's move this expression to the left-hand side and then divide both sides by the mass of skater B. So what we'll end up with is the velocity of skater B is equal to, we have negative the mass of skater A times the final velocity of skater A divided by the mass of skater B. So let's see what we get. We have negative the mass of skater A, we're told is 72 kilograms, times the final velocity of skater A, that's negative 0.2, divided by the mass of skater B, which we're told is 64 kilograms. So if you punch this into a calculator, this comes out to about 0.225, and we're talking about velocity, so we'll say meters per second. So that will be the final velocity of skater B. Now again, in this situation, we know that the initial momentum must be equal to the final momentum, and we already said the initial momentum is 0. So if the velocity of skater A is negative, the velocity of skater B is a positive value, so that the momentum of the 2 skaters adds up to 0. So that will be our answer for that one.